It's your job as a dungeon master to describe the events of your campaign, from the amazing world that you've created to the gritty combats that your players take part in. It's your job to describe how everything looks, feels, smells, and sounds, and sometimes that can be quite difficult. In the early levels, it's not too bad. Say you have a party of level 2s or 3s and they're taking on a gang of bandits. The bandits probably only have 20 or 30 points of health, and your players in a turn are probably only dealing 7 or 8 points of damage each. It becomes quite natural to describe how these things look. It looks a lot like the kind of things you would see on TV or in film or perhaps read about in books. The problems arise as you progress through your campaign. Your party level up, they pick up new spells, new equipment, new magic items, new abilities, and things start to get a bit messier. Take a party of level 12s or 13s. In a single turn, each of them might be dealing 50 or 60 points of damage, perhaps even more, with all the new things that they've collected. How do you now describe what that looks like? It's your job to make sure that each of your players has the opportunity to shine. But as things progress, it becomes harder and harder to balance things out. How do you make a sword swing look just as impressive as a 9th level fireball? Well, it's the hope of this video that we will be able to do this in a mathematical, sort of scientific way. I want to be able to construct a system or some equations that help us to quantify what it looks and feels like to take certain quantities of damage. As we go, I'll be referencing a sort of rough paper that I've written, which has all of my equations and workings out and any kind of references that I make. I'll share that in the description. There'll be a link there where you can access it. You can follow along if you'd like, or you can just read ahead. So let's begin. To work out what it looks like and feels like to take damage in D&D, we need to work out how much force is imparted in a single blow. To do this, we're going to be looking at some Newtonian forces. To begin our investigation, we need to find reference points in-game. These could be things like sword swings or cantrips that we can easily quantify the forces of. Ideally, these actions should be commonly used throughout the game so that we can ensure reliability of our results and have some confidence when extending these formula to the greater game as a whole. I'd also quite like for them to be simple enough that we can approximate them with some basic GCSE physics. I'm not a physicist and I'm barely a mathematician, so we're going to be using a lot of approximations. For that reason, we'll look to the weapons used in D&D. There are two main categories of weapon. There are melee weapons, which are things like swords and clubs, and ranged weapons. These are things like the bow and arrow. We'll also look at the unarmed strike, which is defined in the official rules as a punch, kick, headbutt, or some other forceful blow. By approximating their forces with the help of Newton's second law, we should be able to work out how many newtons of force each weapon applies in an attack. We can then scale this value according to the expected value of the damage to work out an average for the amount of force applied when taking 1 point of damage. We'll then take an average across the three categories to work out a more accurate approximation for the amount of force required to take 1 point of damage. Before we begin crunching the numbers, let's make a list of assumptions we can use to make the maths a little bit easier. The first of which is that damage is consistent in D&D regardless of whether you're wearing any shields or armour. This also means that damage dealt to objects is just the same as if it was dealt to a target. As such, we assume that the force is the same as well. The next assumption is that damage dealt in an area is consistent in that entire space. This means that if you are at the epicenter, you take just as much as if you were on the edge. Similarly, we assume that damage doesn't drop off as you increase the range of an attack. A bow shot from 5 feet away deals just as much as one from 300. Just as before, we assume that this also follows equivalently for the force. The third assumption is that our target has no resistances, immunities, or vulnerabilities, and as such, we can assume that all types of damage impart the same quantity of force. The last assumption is that the wielder of our martial weapons, the swords and the bows, has the physical capacity to multi-class into fighter. This basically just means that they have a 13 in strength and dexterity. With that being said, we can crack on with the maths. We are going to be looking at impact forces. Now this is essentially the amount of force imparted by one object onto another as they collide. The first weapon we're going to be looking at is the longsword as a part of the melee weapon category. To work out the impact force as it collides with a tree, a crate, or a goblin's chest, we are going to be using Newton's second law, F equals ma. However, we are going to be using a simplification of it, where instead of using the acceleration, we'll be looking at the change of velocity over time. And since that final velocity will be 0, we're looking at the last recorded velocity instead. Students at the University of Arizona undertook a study into the impact forces of medieval weapons. They were able to approximate the arc of a sword swing by taking a bunch of linear segments and using those to work out the velocity and forces at play at each time step. The sword swings in question were just kind of a bunch of graduate students slamming medieval weapons into their dorm room beds, which resulted in a handful of quite funny screenshots. But regardless of this, when swinging the swords at full pelt, they were able to record speeds of about 16 meters per second and a total collision time of 23 milliseconds. Using their recorded mass of about 1.8 kilograms for the sword, we can put this into our formula and obtain a final output of roughly 12 kilonewtons of force per sword swing. However, since we are looking at the amount of force of 1 point of damage rather than 5 or 6, we now need to rescale this value. We can do this by taking the expected value of the sword swing. The expected value is a little bit like the mean, and I'll link to a video which explains things better, but for the purpose of this, you can think of it as the damage you would expect to see from that weapon. Using the versatile trait on the longsword, we get that this deals 1d10 plus 1, which has an expected value of 6.5. Dividing this 12 kilonewtons by 6.5 results in a final output of about 1.9 kilonewtons of force, which, according to the maths we've done, should be equivalent to 1 point of damage. Following a similar pattern to the study we've just conducted on the sword, we can also undertake an investigation into the amount of force imparted by a punch. The organisation Boxing Science did a study on amateur boxers and found that on average they were able to impart about 2.5 kilonewtons of force per punch. Ignoring any racial or size category differences in our fantasy setting, we could take the standard unarmed strike rules, which is 1 plus strength modifier, which in our case totals and averages 2. We can then rescale our estimated force of 2.5 kilonewtons by this expected value to obtain an average impact force of 1.25 kilonewtons for 1 point of damage. For the final category, ranged weapons, we'll be looking at the longbow because it is the best sort of documented of the D&D weapons, but I cannot stress enough how difficult it was to find anything about bows. So, oh dear God, if you have a bow and arrow at home, I beg that you publish something about it, something about how fast it can shoot or anything, please, I'm begging you. Anyway, using a very similar approach to the sword that we did for the melee weapons, we can take that similar approximation for the acceleration, and this requires that we work out the mass of the arrows that we're shooting and the final impact velocity. There is a website for longbow enthusiasts, and yes, that does exist apparently, found that the average medieval era arrow shot from a warbow weighed about 1,200 grains. This was an old Bronze Age measurement for the weight of ammunitions and translates to about 78 grams nowadays. For the speed at which these arrows were shot, we looked to the book The Great Warbow. They claimed that the English longbow could shoot arrows up to speeds of about 64 meters per second, which is an astonishing 150 miles an hour. I don't know how much I believe this, but it's all I could find. Putting these together into our formula with an impact time of about 1 millisecond, we can conclude that the force imparted by an arrow shot from a longbow is roughly 5 kilonewtons. Rescaling this using the expected value of the longbow, which is 1d8 plus 1, we obtain our final estimate of 0.9 kilonewtons of force, which in the case of the longbow is equivalent to 1 point of damage. Now that we have 3 estimates, we can take an average across them to hopefully get something a little bit more accurate, and doing so gives us an estimate of 1.35 kilonewtons of force for 1 point of damage. So now that we have worked out this value, this 1.35, which is the amount of force that is equivalent to 1 point of damage, we can start to look at the amount of force that different spells, different weapon attacks, and different actions are imparting when you do them in game. So I've chosen a few of my favourite spells that I like to use against my players, or on the odd time that I get to be one. The first of which is Eldritch Blast. This is every warlock's favourite spell, and it deals 1d10 points of force damage, which when you average this out, you're dealing about 7.5 kilonewtons of force per target. And of course, with it being a cantrip, as you level up, you get more damage dice, but for the Eldritch Blast, you're casting more beams. So at sort of max level, you're going to be casting 4 beams of this and dealing, about 30 or so kilonewtons of force, which is quite hefty. Some of my other favourites are, of course, Fireball, one of the most famous spells in D&D, and this deals 8d6 points of fire damage, and on average is going to be imparting a force of about 40 kilonewtons. And when you think about it, that is quite a lot of force. It starts to add up when you consider it being an area spell. It's a 20-foot sphere, and so you can hit quite a few targets with that, and so depending on how many creatures are in that area, you might be dealing hundreds, if not thousands of kilonewtons of force. There's a few more spells in the paper that I've attached as well in the description, but we'll finish off with Meteor Swarm, one of these quite high level spells. You can call down these meteors, they slam into an area, and they deal about 20d6 of bludgeoning damage and 20d6 of fire damage, which on average is about 189 kilonewtons of force, so almost 200 kilonewtons of force per target per meteor. The numbers we're reaching now are crazy, and you can work these out yourself as well. It's very simple. All I've done is I've multiplied the expected value of each of these spells or actions by 1.35. You could do this yourself if you would like to go through and work out what are the expected values for your favorite spells, but I would guess that most of you can't be bothered to do that, or perhaps don't know what the expected value is. I'll link to a video which explains it a little bit better by Khan Academy, but it's essentially a measure of mean or the average value that you would expect to see. And so I've written a piece of Python code. It's very simple. All it does is work out the expected value of the damage for a spell, and it will tell you how much force is being imparted to those targets. Now that we've obtained these numbers, these estimates for the amount of force that different spells and actions can do, we need to find ways to describe them. The easiest way to do this would be to look at the amount of force an object exerts as a result of being pulled by gravity. We can work this out by multiplying the mass of an object by the gravitational constant, and for the Earth that's 9.81 meters per second squared. By equating the weight force with the impact force, we can rearrange, do some mathematical wizardry, and work out the amount of mass that's roughly equivalent to certain thresholds of damage. So, looking at these different thresholds of damage, we can find objects of varying mass that are roughly equivalent to that under the effects of gravity. So, at about 10 points of damage, you're looking at about 1,300 kilograms, which is roughly the weight of a small car like a Volkswagen Beetle. At about 30 points of damage, you're looking at nearly 4,000 kilograms of mass under the effects of gravity, which is about 4 cubic meters of water. At 50 points of damage, you're looking at the mass of an adult male elephant, and similarly now at 70 points of damage, you're looking at the mass of an adult female T-Rex, coming in at about 9,500 kilograms. Topping us off at 90 points of damage is a cruise ship anchor, which for reference is almost 13,000 kilograms, 13 metric tons of force. Though this provides a fairly useful scale if you are a physicist and understand what these numbers mean, like I've said before, I'm barely a mathematician. I can't visualize what these things mean just by the masses of certain objects. And so now we're going to be looking at some more dynamic examples of forces, things that are in motion. So looking at about 5 points of damage, this is roughly equivalent to the force of 2 American footballers charging full speed into each other at about 20 miles per hour. Jumping up to about 20 points of damage, this is roughly the amount of force that you would feel if someone dropped a standard vacuum or hoover from the top of a house. About 10 meters drop, roughly 5 or 6 kilograms straight onto your head, about 22 points of damage, roughly 30 kilonewtons of force. Then as we progress up to about 40 points of damage, this is roughly equivalent to the force it takes to break steel, industrial stainless steel, about 40 points of damage. Now as we jump up to 60 points of damage, we're looking at 8 times the force it takes martial artists to break those wooden boards that you see them karate chopping through. They would need to break 8 consecutive wooden boards in a single strike to be able to reach about 60 points of damage. And then topping us off at 83 points of damage, this is equivalent to the force you would feel if a car hit you at 30 miles per hour. I think it's fair to say that some of these forces are crazy, and most of us would be tapped out by 20 or perhaps even 30 points of damage. Now we could end there quite comfortably. We've investigated the amount of force that is equivalent to 1 point of damage. We've collected a list of examples that you can use as sort of reference points in your descriptions in combat, but there's one other thing about D&D combat which kind of irks me. In the player's handbook there are a collection of firearms and explosives that just don't sit well with the theme. There's things like antimatter rifles and revolvers, but they don't seem to deal as much damage as they could. Some of them deal perhaps 2d10, a d12. Compared to their real world equivalents, they feel significantly underpowered. And because of some of these strange properties they have, it takes multiple turns to load them and fire them. And by the sounds of things, most DMs just ignore them completely. But now that we have this system in place, we could reverse engineer real world weapons and try to approximate their damage dice in game by using their forces from the real world. To keep things brief, we're just going to look at 3 cases: a firearm, an explosive, and some kind of artillery weapon. The first of the 3 categories that we'll be looking at will be a firearm. And so for this, I've found a study by a US ballistics company. They were shooting a 44mm Magnum revolver at their ballistic shields and found that when traveling at speeds of almost 450 meters per second, these bullets could only penetrate about 2 centimeters. Using some physics, which you can find in the paper linked below, we can obtain an estimated impact force of about 82 kilonewtons, which translates roughly to about 60 points of damage. Now, if we assume that this is the average damage of this weapon attack, we could then find a set of damage die which roughly fit this. These would be 17d6, 13d8, or 11d10. And notably, these are much larger than the 1d10 or 2d12 which you find in the firearms for the player's handbook. To study explosives, we'll need to look at the explosive force. To do this, we need to work out the total energy released by the explosion and then divide that by the maximum destructive distance. Working out the maximum destructive distance is quite easy. Most explosives will describe this somewhere in their documentation. Working out the total energy released by an explosion is a little bit more difficult, but we can approximate this by working out the amount of explosive filler within the weapon. If we assume that it behaves similar to TNT, we can then work out the amount of energy released. Famously, 1 gram of TNT releases 1 kilocalorie, or 4.184 kilojoules, of energy when ignited. And so to work out the explosive force of these weapons, we just need to work out the quantity of explosive filler. An activist group by the name of Action on Armed Violence have a wealth of resources about modern day weapons and their destructive capabilities. Using what they have online, we can find that the M67 fragmentation grenade has about 184 grams of explosive filler. Now, in reality, not all of this would be TNT and would likely be a more explosive compound than TNT, but for now, we'll assume that it's entirely made up of TNT. This means we can work out the total energy released upon explosion by simply multiplying the quantity of filler by the explosive capability. The documentation also reveals that it has an explosive range of about 20 feet, and so by dividing the total energy by 20, we obtain a final force output of about 38 kilonewtons. Using our new formula for translating force into damage, we find that this is about 28 points of damage. Now, the perceptive spellcasters amongst you might have noticed that this is the average damage of 8d6, which is also a 3rd level fireball. It's quite strange that a fireball and a grenade, which appear similar in action, also have quite similar values. They both have the same force output and both have similar ranges as well. The fireball has a 20-foot sphere, whereas a grenade is a 20-meter sphere. It makes you wonder where wizards got the idea in the first place. Looking now to artillery fire, we find that mortar shells, which could weigh upwards of 15 kilograms, typically have about 2.5 kilograms of explosive filler. Similarly, they have a destructive radius of about 30 meters. And as before, we can follow a similar pattern to the grenade, working out the total explosive capability by multiplying the quantity of TNT by the energy released by 1 gram of TNT, and then dividing by the total destructive radius. This gives a final force output of 348 kilonewtons of force, which is crazy. It's nearly 260 points of damage. Now, assuming that this again is the average of an attack, we can find a set of damage dice to approximate what this could do in game. This could be 74d6, 57d8, or 47d10. If you take the average to be 258 for each attack, it would take only 3 mortar shells to take down a Tarrasque, assuming that this is magical damage and overcomes its resistances, which is insane.
So what have we actually done? Well, we've played around with a lot of numbers and been able to create these
kind of loose approximations, these formula that you can use to convert between damage in D&D to real-world Newtonian forces. We've also then been able to build on this and create a kind of loose scale which provides some descriptions that dungeon masters can use to look at the magnitude and the kind of poignancy of some of these attacks that their players are dealing, and also that their creatures are dealing to their players. We then also applied this to create a very small Python code which you can use in your own time to work out the expected value of spells and attacks and things like that. We then concluded with a very brief look into modern weapons and their place in D&D, perhaps drawing some distinctions and some differences between the amount of damage that they deal from the player's handbook and what they might actually deal in reality. Now, of course, this study is not without its failings. This was a very, very simple version of this problem. We've taken a lot of approximations, estimations, we've simplified down the problem to its base components. You could easily extend this looking at derivatives, partial derivatives, and forming ODEs and PDEs to solve these problems, but at the end of the day, this is just for a bit of fun. Now, if you've stuck around for this long, hopefully you enjoy this kind of content, and I'd like to make more of this in the future. So there'll be a link in the description to a Google form that you can submit ideas to if you have things that you'd like me to explore and investigate. I can't promise I'll do them well, but I'll give it a go.